Okay, and welcome back. So let's now go through problem 3 on the back of our simple harmonic motion worksheet. I'll go ahead and read the problem. A 2 kilogram frictionless block is attached to an ideal spring with force constant 300 newtons per meter. At time equals 0, the spring is neither stretched nor compressed, and the block is moving in the negative direction at 12 meters per second. Find the amplitude and the phase angle. Okay, so that's our problem. And again, it's very helpful to draw a picture. The picture here is our most common example in this oscillation chapter because it's our most simple oscillator, and that is a block of some kind, which is, let me try to draw that a little bit better, is initially located at position equals 0, and it's attached to a spring which is attached to the wall. So if you give this some initial velocity or displace it, it oscillates back and forth. So that's our picture, and as always, we define the plus x direction to be the direction where we're stretching out the spring, and the origin to be the equilibrium point where the spring is neither stretched nor compressed. Okay, that's our picture. We can write down some of the knowns. They told us the mass of the block is equal to 2 kilograms. They told us the spring constant is 300 newtons per meter, so that's our lowercase k, our spring constant. And they told us something about the initial conditions. At time equals 0, the spring is neither stretched nor compressed. So I'll call that my position at time equals 0, and the spring is neither stretched nor compressed. That's the same thing as saying we're at our equilibrium point, which we always define to be x equals 0. So our initial position is at x equals 0, and at that moment we're also moving in the negative direction at 12 meters per second. So our velocity at time equals 0 is equal to negative 12 meters per second. So this is a picture of the initial state, but at the initial moment we are moving in this direction with some initial speed. Okay, so at time equals 0, we're at the equilibrium point, but we have some speed, so it's going to end up, kind of compressing the spring, reaching some minimum position, and then oscillating back and forth, and it's just going to oscillate back and forth forever because we're on a frictionless surface, and that tells us energy is going to have to be conserved here. So that's our picture of what's going on, and let's think about our unknowns. So the problem asked us to find the amplitude of the oscillation. All right, so how far is this going to get in the negative direction? And then how far is it going to get in the positive direction as it oscillates back and forth? So that's kind of the maximum and minimum position of this block as it oscillates. And then we have to find the phase angle, which we also call the phase constant, and it's signified by this symbol phi, which you'll see on your equation sheet. And remember, the phase constant or the phase angle is a variable in our equation for the position of this block as a function of time. We know that the position of this block is going to depend on time in a sinusoidal way, like a cosine curve. But in order to define all initial conditions, we're going to have to shift that cosine back and forth, and that's what we use our phase angle for. So those are our two unknowns. So there's a few ways we could solve this problem, and I think the easiest way is to, again, think about all the different methods we have to solve these problems. We have the relationship between force and acceleration, which for a spring gives us a relationship between displacement and acceleration. But that's not going to be too helpful here because we don't know anything about the initial acceleration. But we do have some initial knowledge about the initial position and the velocity initially. When we know things about velocity, that's usually a clue that we can use energy concepts, right? Because velocity is a key component of kinetic energy. And so that's kind of a hint that we can try to use velocity, we can try to use energy in our answer. So let's start by thinking about using energy concepts. The system is frictionless. There's no external pushes or pulls, so the total energy of the system has to remain constant. It can't change. The energy isn't going to go anywhere. It can transfer back and forth between kinetic energy and elastic energy as it oscillates back and forth. but it's not going to go anywhere. So I'll call this kind of method 1 of solving the problem. With method 1, I'm going to start out by using energy conservation, which is saying E1 is equal to E2. Total energy of the system is constant. And we can use that to our advantage because one of our unknowns is our amplitude. And when I'm at my max amplitude, right, when I'm right here, something special happens. At that location, my velocity goes to 0, right, when I'm at that position, because I'm turning around at that location. So if my velocity is going to 0 at that location, that implies my kinetic energy is going to 0 at that location. So if I call that time 1, when I'm at my max amplitude, then my kinetic energy at that moment is 0, and so all of my energy is an elastic potential. And we have an equation for that, 1/2 times the spring constant times our position at that moment in time squared. And our position at that moment in time, we know that's our amplitude, which is our unknown. That's what we want to solve for. That's one of our unknowns, at least. So I'm going to choose to pick that to be my time 1 when we're at our max amplitude, because that's what I want to figure out. And then time 2, I need to decide based on other knowledge I have, and I know something about another moment in time, and that is at this moment in time, when I pass through the equilibrium position, my position is 0 and my velocity is negative 12 meters per second. So if that's the case, this is my total energy at time 2. I have elastic potential energy plus kinetic energy, but my elastic potential energy goes to 0 because I'm at my equilibrium point. My x is 0, and so all my velocity, all my energy is in kinetic, and my velocity is this max velocity, or my velocity at that moment. So when I write it in that way, I now have an equation where I have spring constant is known, mass is known, velocity is known, and I only have one unknown, which is my amplitude. So that's great. I can divide both sides by 1/2, so that term goes away, and I can solve a squared is equal to m over k times v naught squared, and just solve for my amplitude. A is equal to the square root of m over k times v naught. My initial velocity, or my velocity time, equals 0, and we'll note that the mass is 2 kilograms, the spring constant is 300, and the velocity is negative 12. So plugging into this, we're going to get that A is equal to let's see, what does it end up being? It ends up being, let's go ahead and, oh yeah, there it is, 0.98 meters. Okay, you can plug in either negative V naught, negative 12 here, or positive 12. You'll get either negative 0.98 or positive 0.98 for this answer, but that's okay because we are oscillating back and forth between those two locations. So those are the two locations that tell us something about our amplitude. Okay, so we know our amplitude, and now the question is, what is our phase angle? So I'll give myself a little bit more room here, and I'm going to write down our only equation on our equation sheet that includes the phase angle, and that's that our position as a function of time is equal to A times cosine omega t plus phi. Right, so this is our amplitude, A. This is our angular frequency, omega, and this phi is our phase angle. So that's our unknown here. So if this is the only equation that has that phi in it, then it's the only one that we're going to be able to use, right? And remember, we have to have this concept of phase angle because a cosine curve looks like this, right? For every cosine, we are at our max position at time equals 0. And that's not the case here, right? At time equals 0, we are at this location, right? We're at x equals 0 at time equals 0. So I'm going to have to shift my cosine in some way such that at time equals 0, my initial position is correct, right? I also have to shift it so that my initial velocity is correct. So I can see I'm going to have to shift my cosine in this direction so that it now kind of looks like this, right? If that's the case, my initial position is 0, and my initial velocity is moving in the negative direction, right, when I'm plotting x versus t. So that's the point of this phase angle, is to shift our cosine. And so I could actually probably figure out what the phase angle is just by drawing pictures like this, but I also can just use this equation. Right? This is an equation where the amplitude is, fortunately, we just figured out what it was. All right? We know our amplitude. We just determined that it's 0.98 meters. Omega, we actually know because we have an equation for omega. Omega is equal to the square root of k over m. This is one of our key concepts, that the frequency or angular frequency depend only on the properties of the object, like the spring constant and the mass. So that's one of the equations on our equation sheet, and we can use that to find omega. And so in this equation, if I want to solve for phi, if phi is my unknown, and I know a and omega, then all I need to know is, if I know x and t, then I have one unknown, and I could figure out that phi. And guess what they gave us in the problem? They gave us x at a key moment in time, at time equals 0. So we know that at a given moment in time, at time equals 0, we know the position, it's x naught, and that's equal to a cosine times 0, right? T is 0, plus phi. And so plugging in what we have for x naught, that's just 0, is equal to a cosine of phi. And a, it doesn't matter what it is, I can divide it by both sides, and I get 0 is equal to cosine of phi. So I can now just do an arc cos. Phi is equal to arc cosine of 0, and you get the answer that this is equal to minus pi over 2. So that's our phase shift. We had to shift our cosine by some amount in order to properly set our initial conditions such that our initial position was 0 and our initial velocity was negative. So to describe that with this cosine, we had to shift it, and that's what we were able to do here. So that's our answer. That's method 1. And I think this is a pretty general method that could work pretty well for you when solving these type of problems, when you're trying to find, for example, the phase constant. You may have to use energy conservation first, and then use our method that relates position and time. Now, I want to quickly kind of show you another method, which is totally equivalent and maybe a bit more general. We'll be able to derive an equation which you may be able to use in your future. Again, of course, in a test environment, you'll have to, again, show all your work and prove that this has to be the case. But let's go ahead and do it. Right, so this method is what I'll call method 2. Is only going to use our equation that relates position and time. Right, and with this method, we're going to try to solve for both a and phi. We're going to say these are both unknowns. How do we solve for these? Well, again, we can use the same trick we used last time, which is at a given moment in time, at time equals 0, we know our position. They told us that in the problem. And so we can plug in into this equation, time equals 0, and we just get a cosine of phi. And so if we know this, we can hopefully try to solve, but with this method at this moment, we haven't figured out a yet, and we haven't figured out phi yet. So we have 2 unknowns. But what else did they tell us in the problem? They told us the initial velocity. So let's use this equation for position to derive an equation for velocity as a function of time. We know velocity is equal to the dx dt. So I can take a derivative. Derivative of cosine is negative sine. And then I have to take the derivative of the term inside the brackets. So when I do that, I get an omega. So when I take that derivative, I get this velocity as a function of time. Right, omega pops out, and I get a negative sign. So I now have an equation for velocity at all moments in time. And so it told me in the problem statement that our initial velocity is negative 12 meters per second. So I know my initial velocity. And so I can plug into this velocity equation for time equals 0. to derive this equation. And so now I have two equations. This position equation where I know the position, and this velocity equation where I know the velocity, but each has two unknowns, a and phi, a and phi. And yes, we do know omega because we know the spring constant and we know the mass. So these equations, I can now solve for a and phi because I have two equations and two unknowns. And the easiest way to do this is actually to divide the two equations, right? And so let's see what happens when I do that. What I basically want to do is do v naught divided by x naught, or v naught is equal to this, so minus omega a sine of phi divided by x naught, x naught, which is right there, which is equal to a cosine of phi. And so when I do that, I can see my amplitude cancels out, and now I have an equation where that's known, that's known, that's known, and phi is my only unknown left. And so that's wonderful. This becomes equal to minus omega times tangent of phi. And so now I can go ahead and just solve for phi. I get phi is equal to inverse tan, or arctan, of minus v naught over omega times x naught. And so now I have an equation where I can plug in. In this particular example, I have minus v naught with negative 12. Omega, I forget what it is, but it doesn't matter for right now because we're about to multiply it by 0, right? Our initial position was 0. So I'm dividing by by 0 here, and so that's not a good situation to be in. But we can think about this. We're really taking the arctan of minus infinity here. And if you think about what arctan looks like, it kind of looks like this. So minus infinity, this is asymptoting towards minus pi over 2, which was the answer we got before, and this is just another way of solving it. So that's another way of solving for the phase constant, which is an alternative method. I still think the first method was a little bit more straightforward, but this is a very nice method. Now that we know this, we can take any of our other equations to solve for the amplitude. Like we know that this is true, we derived that earlier. So if our amplitude is now our unknown, I can just solve for it. Now that we know the phase constant, we can plug into this equation and find our amplitude. So that's an equivalent and another way to solve this problem that should give you the same answer as we got with method 1, finding the amplitude to be 0.98 meters and finding the phase constant to be minus pi over 2. So with that, thank you, and this will be the end of this video.